So let's start. My name is Kafe Abzarva. Today I will be moderator for this session, and in this session, Kamal Bey will talk about likelihood analysis. And if you have any questions, please do not hesitate to ask or write in the chat box. So at the end, Kamal Bey will answer to your questions. Now, Kamal Bey, can you please start?
Good afternoon, all. Can you hear me well?
Yes, we can
Yeah.
hear you.
Good afternoon again, and Katya, thanks for moderating. So today we will talk about likelihood analysis, and whoever joined us previous two sessions actually, we talked about the hazard identification and different methods, techniques, and if you still remember our risk management process. So during the first 2 weeks, we talked about hazard identification and different type of the hazards like operating hazards, external hazard, natural hazards, and any other hazard. And the last week we talked about the consequence analysis, which is one of the main part of the risk analysis. And now today we will talk about the second part of this, which is likelihood analysis. And these two together, like a consequence analysis and likelihood analysis, should give us together the bigger risk picture. So in terms of the content, I will talk about evaluating frequency. So how we normally evaluate frequency, probability, and I will show you some specific examples of the how we use certain techniques like fault tree and event tree techniques to deliver the frequencies or likelihood for the event. And in the second part of the presentation, if you have got time, and I guess we will have, so we will touch on the human error identification and quantification, because you will have seen that human error quantification and identification of this human error is also one of the main parts for the likelihood analysis. So first part about evaluation frequency, fault and event tree, and second part will be about human error and some technique to quantify this. So when we say evaluating frequency, so if you remember, or you may remember, I am not sure the same group is joined. So when we talk about consequence of the event, we said that some events may be high consequence, but the other could be like a low consequence. But they also should be complemented by the likelihood of the event to better understand what's the actual risk. So what we normally do when we are evaluating the frequency, we use, so there are different techniques. So one, let's say, easier option is to use published database. So I will show you some specific examples for which database you can use. And or the other option is like I use the site specific data. So basically your past experience. So whatever happened to you, it could give you good understanding of the likelihood. But for the certain rare events which have never happened, so you will need to use the synthesis of these two methods, basically using the published data and synthesize this with your site specific data to understand your actual frequency applicable to your site, your specific case. And it shouldn't be a surprise that if you have got high likelihood and high consequence event, there is a red light, it's a worry. And if you have got like a low likelihood, low consequence event, it's generally acceptable, generally okay. But for the combination of the low likelihood and high consequence, or high likelihood, low consequence, we will need to do further analysis to understand if it is as low as reasonably practical or not. So in terms of the first one, which is like a published database, so you can use OGP report 44 series. So we have got like a very good release frequencies. So you can see one of them is related to process facilities release frequencies. The second one is about blowout frequencies. You can also find some storage incident frequencies applicable to that most of the time atmospheric storage tanks. And also there is one specific series on riser and pipeline release frequencies, which could be used for the assessing the offshore or onshore pipeline releases. So that's really like a good, robust data available from many sources, many big companies. But the main question is that, as we mentioned, so it is like a published data. It may not be applicable to your specific site or your specific case. So that's why the main question is that relevant or not? So and we will see how we can use this data basically to synthesize our specific example. And also the second drawback may be about like the way we work. So each company, each like a department, each operator may have got their own like a way of working, own safety culture. So this you can appreciate that this uh, generic published database frequencies may not actually consider the way the actual operator works, or the actual company work. And the other so it's about like a published like a database. And as I said, the second method could be to use your past experience. And I mean, this is really like a simple like a math. So basically method is you count how many incidents you have got and how many operating years you have got, and then frequency will be derived by dividing incidents per operating years. As an example, you can see, let's say you have got 4 leaks from pump seals in 8 years, and you have got 10 pump. So basically, this is 4 incident per 8 pump year, because you operated 10 pumps for 4 years, for 8 years. So basically, it is 0.05 leak per pump year. So this is basically past experience. So in published database, you will find generic frequencies. In your site-specific example, you can derive your own frequencies. But also, as I said, for very, very important rare events, we use certain techniques to synthesize these two together to understand what could be the frequency for our specific case. So with past experience, so let's say in this specific example, yeah, we have got like a 4 incident out of 8 years operation for 10 pump. But uh, you know, it's in terms of number of incidents. So it's about whatever you see in the reports. So maybe there is a possible underreporting. You know, someone has seen some event and didn't consider even that it's important and didn't report it. And in terms of the actual consequence of event, you may remember last week we talked a lot about the consequence modeling to understand how bad it could be. And I think it shouldn't be a surprise that all incidents are not equal in terms of its consequence. So it may be like one of them out of these events could be like a simple SIP drip, and the other could be catastrophic seal failure. And then this is the actually issue we normally face when we do past experience methodology. And how many operating years? So we say that we assumed like we have got 8 years of operation and 10 pumps, and we said 80 pump years. But maybe some of them actually was locked down maybe for many years. So maybe one of them, two of them is arranged as a due to standby, and the second one was not operating for most of the time. So this is like these two factor can change the number of the incidents or number of the years to derive the actual failure frequency. And also in terms of taxonomy, so do we assume that all pumps are equal? So maybe this is one of them is like a big mainline pump, pumping crude oil from one country to another, and the other is like a small transfer pump transferring certain amount of I don't know, produced water from one part of the plant to the other part. So should we consider them separately, or we can treat them equal? So this is the issues about doing likelihood analysis for using past experience. And how we should, the categorize, as I said, the failure itself. So what's the minor failure, what's the catastrophic failure. So these kind of things actually may change the actual result, and you may have like ended up with the frequency which is not reflecting what you have got at site. And when we are doing likelihood analysis, so two main actually concerns. So First question you should ask yourself, the data or the source I am using, is that relevant? And the second one is robustness. So how robust the data. So when we are evaluating frequency or likelihood or probability, so it's really balance of the robustness and relevancy. So sometimes you may find like a data which very robust, like in you will see have seen in OGP reports. So very robust data, but usually this robust data is less relevant to specific issue you are chasing. And on the other hand, when you are using like a very relevant like a data for your specific case from your specific site, it's really most of the time is less robust because you do like a some past experience mass behind that. That's far. There is always there uncertainty when you do like these two methods to understand the likelihoods. But how you can overcome this? You should like okay, obtain always best available robust data you can have, and then you should really assess whether it is sufficiently relevant to your case or not. And if not, basically you need to just decide what frequency modifier should be added in that case to make it relevant to your specific case, your site. And of course, in engineering and especially in technical safety engineering, the most important thing and one of the important thing actually is documenting all the source, assumptions, and manipulations because they can be a game changer. So, so when you have got like a site data and you can use industry data, and as I said, when you use site data, it may be relevant but not robust enough. When you use industry data, most of the time it will be robust and very robust, but it may not be relevant. So that's why, so to make it a balance between them, you should use a synthesis technique we are using to basically make it balanced for your specific case. So for this specific purpose, we utilize logic diagrams like a fault tree and event tree to evaluate site-specific event data using industrial robust data and modifying them to our case. And basically, synthesis methods like FTA or ETA can be used basically to evaluate rare events, which is robust, relevant data are not available because you may want to investigate one case which maybe never happened. Then so you cannot use your past experience and industry experience may not be relevant. So that's why we use like a fault tree and event tree to synthesize this to um, uh, modify this for your specific case. But just be in mind that when you will need to use these cases as an engineer or maybe even as a student, I don't know. So this developing fault tree or event tree is really resource intensive thing. So it requires a lot of effort and a lot of time. So fault tree and event tree. So how we use them and what are they? So they are like they are product for this synthesis method. And fault tree, so all as you see in the left hand side, so this is all routes to the top event. So basically anything happens there in the very bottom section can lead to the top event. And in event tree, so this is basically from this top event what outcome can be. So here, for example, we have got hot water heater explosion case. So what we say that hot water uh, can be exploded due to relief valve, pressure valve failures, or high temperature, high water temperature. So then we add different causes for each of them, and basically, as you can see, for relief valve failure, this is either relief valve frozen or one of the this happening, so that relief valve discharge line plugged. So line frozen, line cramped, pipe plug installed, and high water temperature should be happening. And how it can happen: regulator failures or high temperature cutoff failures. So then what we do, we we sometimes we do quantification on that. So we quantify this tree to understand what's the frequency of hot water heater explosion. And then once we have got this fault tree developed and quantified, from this event, we develop event tree, and all outcome are happening from the initiating event. So we say that, for example, this happened, temperature surge, yes or no, cooling system failed, yes or no, secondary cooling, yes or no, then we have got consequence. You can see there is a different consequence, like in that case, there is no fatalities, no fatalities. In that case, there is one fatality, and here there is greater than 8 fatalities. And of course, as we quantify them, at the end of the day, you will have frequency for each of them. So you can see, for example, this one fatality case is 4.5 10 to minus 3. The frequency of this can be happening. So this is like, again, two different methods we use to synthesize the data to derive the likelihood for our event, and fault tree from root to top, and event tree all outcome from the initiating event. And as I mentioned, most of the time the purpose of doing this, developing this tree, is to quantify them to understand the actual frequency. So then, as I said, so someone can ask the question that, okay, why we should do, just spend all this effort to develop fault trees, like event trees. Why don't we can just go to, I don't know, one of the OGP report and say that what's the failure frequency of the crude oil storage tank. So the main advantage of using fault and event tree are they are really alternative to the historical data. So they can derive a frequency for an event which never happened. Let's say there is no historical data. So this event maybe not never, maybe this hot water explosion never happened, but we are trying to understand the frequency of this event happening. So to see if you have got high risk or low risk or medium risk. And uh, as you can see, this can reflect the factors to the which specific to the operation or its location. Maybe in one side there are two relief valves, in the other side there are two high temperature cutoff valves, and in the third one there is none of them. So if you go and use the historical data, you cannot say that blindly, the failure frequency of all these three are same, because they are equipped with different safeguards, different protective layers. So basically, you need to reflect the factors which are specific to your operation. And also, when you quantify these things, so you will see that which are the most important contributors. So when you quantify this, you will see that which of this failure element actually is the main contributor to the overall frequency, and also in the event tree. So when you quantify this, you see that out of most time this event will result in no fatalities, and there is a certain chance of having one fatality. So this is the also one of the great advantage of using synthesis technique. So basically it will identify the routes to accident and which are the most important contributors. And also, of course, once you identify this, once you quantify this, it will help. It can help you actually to identify the appropriate mitigation measures. Because when you quantify this, and if you see that main actual contributor for this tree is high temperature cutoff fails, so it will be obvious that you need to worry about this, and you need to take action actually to improve this, rather than focusing on the relief valve frozen case. And also can quantify the benefits from mitigation measures, and help in certain countries, as I mentioned earlier. So you need to demonstrate that you have got risks are alarm as low as reasonably practical. So basically with quantification, you can show that, for example, this case is less frequently, so it's alarm. You don't have to worry about this. Let's focus on the other one. So in terms of the actual method itself, so fault tree methodology. So as I said, first you need to specify the top event. So what's the event you are looking for? So in that example, we are looking at, for example, hot water heater explode, and it could be anything, anything you can think of. So I don't know, you are driving a car. So let's say your top event is car will like a fail at road. When you go somewhere. And then you need to identify immediate precursors and in what combination. So we call this combination like a gates. And I'm sure that you have some familiarization from probability theory. So what does and mean? What does or mean? And you will see many and on or gates in fault tree methodology. And we use sometimes Boolean algebra. I will mention this in the presentation as well. And then when systematically you need to work down until the end of the tree. So basically which we call base events. So to understand what is your base events, and you stop at base events which there is no, the tree further cannot be developed further in a meaningful way. So where there is a adequate data on base event. So for example, in that case, once you reach this base case event, if you have got enough information how much time relief valve is frozen or what's the failure of the cutoff temperature, uh, let's say RTDs, and then these things should be enough for your base case. So there is no further meaningful broke down. But as you see here, relief valve discharge line plugged. So you can further break it down because it could be broke down. Plugging can be due to frozen, due to crimped, or due to a pipe plug. So you can further actually break down this. So basically, you will stop at base case where there is no further meaningful breakdown. And then you basically quantify base events, and then you quantify all these base events, what's the frequency or probability for each. Then based on that, and using combination of these and or gates, you calculate frequency of the top event. So as I said, we use some logic gates. So one of them is actually, two most popular are OR and AND gate. So OR gate output occurs if any of the inputs event happens. So this is either this or this. And I'm sure that you know from probability theory how we sum up their frequency or probability. And AND gate happens when all the input events happen. So these first one and second one and third one. So if there is an AND gate, so which means that all three shall happen so that events can happen. And for certain big, actually specifically for the big logic trees, you will see this triangle, which means the transfer gate. It's just to indicate that there is no like a operation on that. It just indicate that part of this fault tree is developed to somewhere else because of the size. So it's like a typical and example for your understanding. So to fire an explosion to happen, so if you ever heard the fire triangle, so you need to have fuel present, oxygen present, and ignition source present. So this is basically AND case. So to fire to happen, there should be ignition source present and fuel present and oxygen present. So that's why event only occurs when all inputs happen. So OR gate example, let's say you have got high level trip on your tank. So it can actually fail if the sensor fail, which is the sensor actual level in the tank, or switch, like a physical switch. So either of the failure would result in the high level trip failure. So basically this will be this sensor failure or switch failure. So output occurs if any of the inputs happened. So tree construction. So I will not spend this actually too much. So I would normally do this when we are in a physical classroom. So let's say, for example, my example was that let's say there is a car, and basically car is stranded due to flat tire. So how you would develop this fault tree, bearing in mind the 6-step we identified. So basically you need to specify top event, stranded car, then identify the immediate precursors. So how car can be stuck in there. So it's about either you don't have, I don't know, spare tires, or you don't have tools to replace your tire, or you don't have like a competency. So maybe some driver are not like competent to basically replace the tire. So then basically you will systematically go down to the base event and quantify this. And tree quantification, As I said, so tree quantification is always based on the event, and basically you need to work from down to up, and sometimes you need to use Boolean algebra. So I will tell you what's the Boolean algebra in a minute. But before that, actually, frequency or probability. So you will have heard this many times. Like sometimes people will say frequency, and sometimes people will mention probability. You need to be very clear on frequency and probability when you are dealing with the fault tree analysis. So frequency is basically the number of occurs over a given time period. And in industry, we usually use a year as a time frame. But probability is expressed as a number between 0 and 1, and it's just a fraction, and which means that if the probability is 0, it nevers, and it's a 1, it is certain. So basically, probability of component is failed, probability of person incorrectly performing a task. As you see in frequency, there is a time frame definition. It's always over a given time period, and usually it's per year. But in probability, there is no time definition. It's just expressed fraction as a fraction. So when you use frequency and probability in fault tree, so basically at the end of the day, you are interested to determine the frequency of the top event, which is in the top of your tree. So base events and intermediate gates, so they could be combination. Some of them could be a probability, but some of them could be frequency. But they are definitely governed by certain rules, which I will tell you in a minute. And each minimal cut set should have a frequency, because finally at the top you should have frequency, not probability. And frequencies are usually assigned those which initiate a path to the top event. So if you look at a tree, you will see that there are certain route to the tops. So basically, you assign a frequency for this path, and probabilities are usually assigned those which is like a enabler, which either allow or the stop path to further develop the top event or stop from development. And sometimes you will need to determine your probability, which will be derived from the failure rate data. And I will show you some example. So this is the example actually when you need to derive a probability from frequency. So let's say that you have got one instrument, I don't know, let's say level transmitter or pressure transmitter. So it is, let's say it's working, and if it's failed, so there are two different cases. So some failure are revealed, which easy to identify that or easy to observe that they are failed. Yeah. For example, let's say you have got car and you are driving. If your tire is like a tire connection is broken, it will be revealed. Yeah, because you will immediately feel that the tire is out of service. But or let's say you don't have fuel. But for certain failures cannot be unrevealed immediately. So something may happen, may fail, but as you don't use this, or as there is no any indication that it's failed, so it may sit there for months and you will not know that it's failed until you use this. So for these two different things, for revealed failure, basically let's say it's a working and it is failed, you need certain repair time, then you repair it and it's working again, and it's failed again, you repair it. So basically probability of failure will be failure frequency times repair time. Yeah, let's say if it operated 100 days, and out of these 100 days you needed 3 days, 1.5 each, to repair this. So basically this is 3 out of 100. So probability of failure is 0.03. But if it is unrevealed failure, so as you cannot reveal until you test it. So let's say you have got an equipment. In our specific example, let's say you have got level transmitter. Yeah, it is working, and you test this every 6 months, let's say twice a year. Yeah, it's working. It may fail somewhere till the next test. You don't know, but when you do test at 6 months, you know that it is working. Or if it's a failure, you fix this. Then again, it increases the failure frequency from working to failed state until next test, and you test it again. So if you look at the between failure and working time, so basically probability of failure will be 0.5, like a 1 over 2, and I think it should be clear for you why I meant 1 over 2, because until you test it next time, half of the time it may be in a failed state because it's an unrevealed failure. So basically you do 0.5 times failure frequency times test interval, which means that if you test it more frequently, the probability of failure will be less because you can reveal this. If you test it in every 3 months, you can reveal this after 3 months. But if you are testing this every 2 years, you can reveal this after 24 months. And in terms of the gate by gate calculation, so AND gate, so you can do, so frequency can be equal to frequency times probability or probability times probability. So frequency times probability will give you frequency, probability times probability will give you probability. But in AND gate, you cannot use frequency times frequency because it's a per year, it's per year, so it will not make any sense here. You have having a per year square. And in OR gate, you can add probability to probability, you can add frequency to frequency, but you cannot add probability to frequency or vice versa, due to obvious reason, because one of them has got unit, but the second one hasn't. So this is like a gate by gate example. So let's say that you have a storage tank and you are filling this tank every so many times. So let's say you are filling this 5 times per year. Yeah. And you have got level automatic gauging system there. And so this is a small fault-free event developed for this specific example. So let's say you have got tank overfill event. So how you can overfill this? So first you need to fill this above normal level, which is done 5 times per year, and should be high level alarm also should be ignored. So how can it be ignored? It could be either alarm fails. So let's say that you have got alarm, but as it's like a mechanical device, it has got like a failure frequency as well. So let's say that 0.02 it can fail. And there is also operator which can some ignore the alarm or miss the alarm. So as here, so how it can happen, it is either alarm failure or operator failure. So it will be OR gate 0.02 plus 0.01. And this tank overfill can happen this and this. So both should happen. So it will be 5 times 0.03. So basically your tank overfill frequency will be 0.15 per year. So which means that every year we have got 0.15 frequency to overfill this, or in other words, in every 7 years you will overfill this tank. And in terms of Boolean algebra, as I said, we are using AND OR gate. So and in Boolean algebra, the maths are not actually simply same as the maths we are using. So in Boolean algebra, so let's say you have got two events like A and B, and let's say you have got AND on OR gate, yeah? So in Boolean algebra, A plus A is equal to A, because you shouldn't really, give credit for the same thing twice. And A plus 1 in Boolean algebra is 1, because if something is obvious, it should be, the frequency probability should be 1, shouldn't be more than 1. A plus 0 is again A, so this is the only thing makes sense in Boolean algebra. And A times A, again, it's A in Boolean algebra, because it's this happening, A happening and A happening, so it's A happening anyway. And A plus not A is 1. So it is obvious. So it will be certain. A times A not happening is 0. So you don't have to memorize all this like a Boolean algebra, but just bear in mind that there is a strange algebra behind fault trees we are normally using when we quantify the fault tree analysis. So this is the example for the same event, actually, for the minimum, the tank overfill event. So let's say you have got tank filled above normal level, as we discussed. Yeah, we have got different figure. So from mass perspective, how it should be, this is A plus B because it's OR gate, yeah. Then it will be A plus B times C, yeah, because this is AND gate. And this will be A plus C times B plus C if you open the parenthesis. And then it will be 0.02 times 5 plus 0.01 times 5, and it will be 0.15 per year. So you can see that this is actually exactly the same as the mass we did. But in complex fault tree, you will need to use Boolean algebra because you cannot do mass on the all fault tree analysis. So this is the example actually we used in our stranded car. So let's say our car stranded with flat tires. And what was the reason? First, flat tires occur and unable to replace the tire. And why we are not unable to replace the tire? Maybe simultaneously the second flat tire, or there is no any spare tire, or we are unable to remove the wheel. And why? Then another sort of the basis cases, and how first flat tire occurs. So let's say there is a puncture by the sharp object on the road, or rupture by the blunt object. So then you can ask why we need to use Boolean algebra, why we cannot just use like a simple math, like using or and like a summing this, multiplying by and. So the only reason is that if you look at this math, so you can see that certain actually things, like for example B, grass on road, glass on road. So it is repeating itself on different place at different location on the tree. So there is B here as well, and there is B here as well. So if you do simple math, basically you will count B twice. So that's why, or another example is, yes, C, pothole, pothole. You have got pothole here, you have got pothole here. So there are two actually solution to overcome this. One is using, as I said, Boolean algebra. With that, you will not repeat the things. And the second one is you can just basically restructure your uh, fault tree so that in every set there is only one and unique event which is not repeating itself. So as you see, so here we have got like this two contributor, like a rupture by blunt object, which is pothole and heat curb, and we have got glass on road here, pothole here, glass on road here, pothole here, which is repeating itself. So we can just restructure the tree, and we will use them once, which where you can use like a simple mass. So this is about fault tree, and moving on event tree actually. So on event tree, so once you identified your fault tree and quantified your top event, so you can basically use event tree methodology to identify the your actual outcome frequency. So how we are doing, we are identifying the initiating event and assigning frequency. So which, as I said, can be the top event of the fault tree with its frequency, which already done. And you basically place in the extreme left side of your diagram so you can further develop it to right. Then you can identify the factors which determine the outcome. So you will have a series of yes or no question, and based on that, write this as a series of like a question along the top of your diagram. And then basically you construct tree based on this. So basically you construct vertical lines yes or no to each question in turning left to right. And then you assign probability where applicable to this case. And then you describe the outcome and determine their frequencies based on the number you assigned. So here an example, event 3. So let's say you have someone else did like a fault tree analysis and identified its frequency. So it's like a freight container dropped off your platform and the frequency is 0.03 per year. Then you ask series of questions. For example, does it strike worker? Yes or no? And probability of yes 10%, probability of no 90%. Then does it rupture pipe work? Yes, no, probability of the yes, probability of no for each. And if the release ignite, probability of ignition, and the rest. And then based on, so you do math like 0.03 times 0.1 times 0.03 times 0.7. So basically if this event happen, if this top event happen, so with the frequency of 6.3 to minus 5, it will result on 10 fatalities from file and 1 fatality due to impact, actual strike of the worker. And 1 fatality if it's not ignited, 1 fatality due to impact because it's not ignited. And in this set, 1 fatality again due to impact. In this set, doesn't strike the worker, but ruptures and ignite, 10 fatalities due to fire. And in the last two example, no strike, no ignition, no fatalities, or no strike, no rupture, no fatalities. And you can see that when you, thanks to math, when you sum all of these frequencies, it should be equal to your initiating event frequency. So this is like a example. So why when we use event tree? So let's say you have got a release source, and let's say you have got either flammable or toxic release. So, and if you have got like a different offsite population and with different windrows with the probability of the wind. So then basically you do this event tree to understand, for example, for this offsite A, when release happened, if the wind, where is the wind coming from, what's the hazard range, and what's the impact frequency on population. So based on that, you can understand if there is any risk about offsite population, which you need to worry about. So basically, this is like a event tree for that specific example. So chlorine release 1.2 per year, wind towards A. So from rose, it is 0.2, and wind towards B 0.5. Then stable weather. So because each weather has got like a different hazard range, and then basically you can see this is the frequency population A affected, frequency no site impact, and frequency population B affected. And again, if you sum of all them together, it should give to you initial frequency. So as I said, when we evaluating the event tree frequency, so probability at each branch may be conditional to the previous answer. So that's why you need to be careful for certain things. For example, winds towards A, and for B, it's like a subtract of the rest. And you need to describe all final outcomes, frequencies given by product of initiating frequency. So here you should say clearly what's the impact, like a population A affected or 10 fatalities, so that the outcome should be clear. And as I said, just for your check, once you complete your event tree, you just need to sum of your all frequencies to understand if it is equal to your initial frequency. If it is not, there is a mass error. So when then question could be what's the benefit of actually doing all this event trees? So basically it portrays graphically how events may develop. So you have got better uh, illustration of the event happening from like a release to the event. And sorry, it easy to understand, easy to audit. So you can see that it's actually this one page graphic is better than maybe two page report. And it describe basically all the outcome. That's why you can see which factors promote or prevent different outcome. What are the main contributor? And also it helps to develop and quantify mitigation measures. So it's really common benefit of the fault tree and event tree. So basically you need to understand which one has got higher frequency, which you need to focus on. In terms of the overall summary, so when we use the synthesis method like a fault tree, event tree, and again, as I said, fault tree is all possible route to top event and construct from top to down, but quantify from the bottom to top. Because you need to first construct your top tree to understand what are the different factors. Then you need to quantify from the bottom to top, basically to do all calculation like using and, or, and Boolean algebra to understand your top event frequency. And in terms of event tree, all possible outcome from initial event, and you just ask series question from left to right to determine root, and basically initiating event frequencies at any branch with probability of the or frequency, basically to determine the outcome frequency. So this is actually all for first two item, like a fault tree and event tree. I will pause here for a minute or two to see if there is any question or that on that. Otherwise, I will move to the second topic, which is the human error identification and quantification, which is also related to the likelihood analysis. So any question so far?
Actually, we had the one question in the chat box.
Oh, sorry.
Rasul Amirov asks, can you please explain transfer symbol?
Yeah. Okay. So do that. Let me go back to the other presentation actually.
Like, he say, I understood it. Like now.
I can skip. Oh, not this one. Sorry. Uh, yeah. So I'm struggling to. Yeah. Here. So basically, what actual transfer gate. So when you look at actually your like a fault tree or event tree, so in real life, actually your fault tree will not look like this. So it will be many, you know, maybe like a 50, 60, 20 contributors. So and it's not like a easy to show this on a like a one pager or one graphic. So basically the transfer is simply saying that certain part of the fault tree is continued to somewhere else. So it's not like any mathematical or operational gate. So it's not doing any calculation. It's just saying that it continues somewhere else. And I think now it should be more clear. And if no any question, moving on human error, and I will try to finish this maybe in maximum 20 minutes. So we already talked about evaluation of the frequency and fault and event tree, but if you look at our overall risk management process, you may realize that one of the hazard actually is human error. So people are not perfect, so they are always doing a mistake, and this mistake can bring some contribution to the likelihood. So that's why, same as doing like a fault trees, event trees to understand the equipment failure, we need to also equally consider the failure of the humans, like human frequencies. So for this purpose, so again, so we know that we should manage the manage human factor side of this as well, because it's not only about the level switch failure, it's not about the PSP blockage, but sometimes people also do mistake. And so that's why we need to manage human factor so that likelihood of the hazard being released is reduced. Yeah. And or limit the consequence of the error, which will happen error recovery or by emergency response procedure. So it's about prevention need or mitigating the consequence by eliminating or by reducing the human factors. So definition of the human factor. So if you look at the UK HSE, human factor definition is that environmental, organizational, and job factor, and human and individual characteristic. So it's not about the actually only human and individual characteristic. It's also about environment they are working. It's about organization they are working, and it's also job factors, performance shaping factor they are doing, which influence their behavior at work in any way which can affect health and safety. So basically, we call the when we say human factor, we refer to the anything can result in health and safety event due to environmental, organizational, job factor, or being human and individual characteristic, which influence your when you say your operator actually behavior at work in a way that can result in an incident or accident. So when we classify actually human errors, we talk about errors and violations. So they are really totally different. So in violation, it's basically you knew that it was wrong, but you do this. Sometimes you do this because you are a bad guy, or uh, sometimes you do this because you didn't realize the consequence. So you didn't realize that this could be a bad day. But in terms of errors, so errors are mainly under three categories. So lapse, slips, and mistakes. So basically, lapse is like you forgot to how to do the right thing. So it's not like a violation. It's not an intent. But so basically, you don't know how to do the right thing. But when you do slips, so you try to do the right thing, thinking that this is the right thing. But when you do mistake, you think that it is the right thing to do. So I will show you some example, and I'm sure that after this example, it will be much more easier to differentiate between lapse, slips, mistakes. And I'm sure that the violation bit is really clear. So because it's like you knew that it was wrong, and that's it. So this is one of the example. So I don't know remember which site was that. So they initially put 4 pump, like as you see, 1, 2, 3, 4, and they leave some space between due to different reasons, just for like separation, so that if there is a fire, let's say, it could only result in engulf the second one and doesn't escalate to the other one. Then their production rates increased and they added like a fifth pump. Now you can see their pump numbering is 1, 2, 3, 4, 5 instead of 1, 2, 3, 4, 5. So slip is automatic action. So you go to the third pump and you go to this fifth pump. So you meant like A, but you did B. Lapse is you forgot the first one. So let's say you need to first do one and then do second. You forgot the A and you go to the B. And mistake, it is deliberate action, but it is not, you don't know that it's a wrong. So you start with second because you think that this is how you should do this. So you think that your procedure says that first go and do B. So this could be due to wrong information, due to misunderstanding, due to your own interpretation. It is deliberate action, but without knowing that it is wrong. So again, in slips, so let's say you have got 2 pump, A and B, and you need to take isolate pump A, and your procedure on your paper say that go and isolate pump A. You go and instead of A, close discharge of the pump B. So you meant to do isolate the pump A, but somehow you ended up with B. So this is slips. This is automatic actions. In labs, let's say you need to first isolate A, then to isolate B, but you forgot to do A and you just directly jump to the B. And mistakes, you just did B because you thought that you should do B. This is the right thing to do. It could be again due to wrong information, due to misunderstanding, due to many reasons. So this is about errors. But and as I said, the other part is violation, which is really clear. So you know it's wrong. So some of them are unintentional wrong because you did it because I mean you. So the main actually concern from human error perspective is intentional wrong thing, because some people do wrong things, some people do shortcuts on procedures outside because they really didn't realize the consequence. They didn't realize that it could result in fire, explosion, and bad day. So then the actually most important question are why these things happening? Why do people make error? Yeah. So you can you may have heard due to if you looked at any investigation videos. So as a suggestion, you can go to YouTube and look at the CSB videos. So this is like a chemical safety board in US, which did a lot of investigation on the incident happened. So from people you may have heard that they always said that I didn't know that it could happen. I didn't understand. I didn't see this. I was confused which one should do. I was tired. It was a fatigue, or some of them said, okay, who cares? But how we can reduce errors? So if they say I didn't know, we need to make better communication. When they say I didn't understand, we need to better train them, better educate them. For I didn't see, we just need to improve the visibility of the workplace. When they say I was confused, you need to proper task management, break tasks to the further if it's a big enough to deal with. So when they say I was tired, so it's about fatigue, it's about people management. But for didn't care, it's really serious and it really requires safety culture and systematic motivation. And if you look at the performance making factors which people affected, so so this is about like a performance making factors is the factors actually shaping your performance doing carrying out task, and it's always depend on the familiarity with the task. So you can appreciate that it is different doing the things for the first time or for the 100th time. So time allocated for the task. So you will have different results if you have got 5 minutes for doing one things or 1 hour for the same. So design of the plant. So our pump example. So I'm sure that if you send 10 people, random people to here, they will think that this is the pump number third. And interruption during the task. So how stressed, how allocated you are on the task when you are doing this. And also there's also one study on demand and efficiency level. So if there's a less demand on people, they find things boring. And if there is a balance of the demand, you will get more out of from people in terms of efficiency because they will find this interesting and demanding. But on the other hand, if you put too much demand, still people then again people will start to deteriorate in terms of the efficiency and finally breakdown. So when we are doing human error quantification, so we are trying to putting a values to the errors so that we can quantify them in the fault trees or risk assessment or likelihood analysis. So for example, if person doing routing simple without stress, without hash, if he has got times enough time, we say that the probability of error is 1 in 1,000. And error of omission, so like this A B C D, and he forgot to do C, he do A B D. So we say that there is always 1 in 100 chance. And non-routine complicated, there's always higher chance. And if you have got even higher stress with the non-routine, so it will be even much higher error. And we say that if you have got high stress and time constraints, you will definitely make an error. So there are different actually techniques we use to do human reliability analysis. So one of them is hierarchical task analysis. So basically to identify what should be the hierarchy of the task. And the second tools are for reliability analysis. So where we are trying to understand the human reliability. So you see therapy's technique for human error rate prediction. So with that, out of one task, you do this exercise to understand what's the human error rate out of this activity. There is also HART, which is human error assessment and reduction technique. Again, so you do same sort of human reliability analysis. So SLIM is success likelihood index method. So with this method, you are trying to understand what's the success rate out of this activity and how you can improve this. And Athena is a technique for human event analysis. So again, you are trying to understand the reliability of human when carrying out the task. So out of them, so I will show you first actually hierarchical task analysis. So what does it mean and how we use this? And from human reliability analysis, so one of them as an example, so you can have understanding how we are quantifying human error. So hierarchical task analysis. So as I said, we use this actually managed and developed procedure for task-based activity. So let's say you have got a task, I don't know, let's say pig receiving or changing out filter or putting standby pump online. So anything, yeah, or simply like making a cup of tea at your home, yeah. So this could be a task as well. So what's this step for hierarchy for making a cup of tea? Like boil water, have a tea, put tea into the cup, put water on the top of it, put some sugar, and that's it. Yeah. So there is certain task, and this is like a one certain step with a task. Yeah. And as I said, this could be as simple as this can making a cup of tea, but it, some like a critical task we are doing at real world, like a starting one natural gas compressor. Yeah, so which is like a quite extensive task. So when we use this hierarchy basically to develop the procedure, so first we put achieving preconditions. So for example, here our task is isolate level transmitter for repair. So let's say you have got a level transmitter and your task is isolate level transmitter for repair. So basically what you are saying plan 0 and do 1, 2, 3, 4 in order. So then you put your preconditions. So what precondition you need to do this? So for example, I've got instrument technician, calibration device, instrument isolated, or etc. So then you put like this your steps. So put it into the manual mode, isolate instrument, depressurize instrument, verify isolation. So then for each of them, you basically develop your further like a sub steps. For example, how you can put into the manual, go to correct controller, change the set point of the current value, put the control in the manual book, and make into the entry. And how you can isolate, identify the correct instrument, close the isolation valve, top isolation valve, close the bottom isolation. So you do basically same for all of them. Then it will when you convert this a document, it will make your procedure like your step 1 1 1 2 1 3 1 4 2 1 2 3 2 4. So it will be nice hierarchical task, hierarchical procedure to achieving isolate level transmitter for repair. So then you can issue this as like a operating procedure for your folks at site, and they use this to basically during their daily activity. And in terms of the human reliability analysis, as I said, we can use many, and not only actually this four method. There are many other different methods as well. But the strength of there are some of them has got very good advantages, but most of them has weakness as well. So for example, TERP is well used, powerful, auditable, and work well with like when you want to do quantitative risk assessment. But weakness is that you need really have like an expert in room, a human factor expert to understand to judge your certain values. And in terms of performance shaping factors, limited range of the performance shaping factors are addressed. And compared to TERP, heart is relatively simple, low resource, but again, expert judgment is required. I mean, what without going actually each of them, I can summarize you all that. So when you are quantifying human error, it is not really an easy task, and most of the time, expert judgment is required for quantification of the human error. So I will show you, for example, one example. This is like an example for TERP, like a technique for human error rate prediction. So what you do, you define the system failure interest. For example, you have got omission, selection, and timing. This is the error type. You omit, you can omit, you can select wrong thing, you can do wrong timing. And what's the performance shaping factor? So omission is like a checking. If you check, you may not omit. For selection, environment, your work environment can affect you. And for timing, again, environment and manage can you. So then these failures are the function of the system, and then we basically try to quantify them. So how we quantify them? So in stage 2, we list and analyze all the human operation and identify human errors, and based on this, we basically process with error of omission, error of commission, error of selection, error of timing, etc. So this is like an example. So basically, you need to estimate relevant error probabilities for each subtask. So let's say we have got uh, A, B, C as described here. Let's say you have got like a 3 error type, and then you quantify each of them, and finally you will have something like that, which can be shown as a very like a resource intensive and too much numbers. And what you do when you estimate the effect of the human error, so with the compilation of the reliability analysis, so you can assess the contribution of the each error, so which one actually is contributing much. So I know this like a this human error quantification is a bit like a maybe difficult to digest. So I'm not trying to make you expert on the human error quantification, but I just want to you know that what like methods are in place and what are the pros and cons of this method when you do human error quantification. Then when you have got like a frequencies. So you can also see and quantify the effect of the performance shaping factor. For example, for omission, let's say your generic frequency is 0.1, which means that you will do omission mistake every 10 times. But with the checking, so let's say you can add second person checking the thing, independent verification, and this thing will change the things from 0.1 to 0.05. So instead of every 10 times, now you will do every 5 out of 100 mistake. So this performance shaping factor will change actually your mass a lot. So you can see 0.05, 0.1, 0.1, then your success factor is actually changed a lot. So then when with this, you can also see which of the, you can also based on numbers, you can also recommend what changes basically required to make this actual task more safer. And then based on that, you can recalculate the failure frequencies here. So you see that. So so there are three actually like step, like omission, selection, and timing, and you can see the frequencies. So for first one, it is 0.05, 0.1, and 0.021. So when you put this in the tree, you see that your success is 0.66. So out of 100, so you are doing 66. So, and if you look at your number, you will see that actually you are doing very bad in that area on the third task. And then you can add your certain another things to make this step, this actual node, more safe. So you cannot, I don't know, any independent check. You can make process condition better, environment better, management better, and then you can see the effect of this on your tree. So if you add like an environmental and management factor, so now it will be 0.1 instead of 0.225, and now your success factor will be 0.77. So it will be increased like a dramatically. So with that, actually, I would like to pause here. And again, for the last bit, as I said, I'm not trying to basically make you like a human factor quantification, human error quantification expert, but I would like to show you. That's why I actually skipped this presentation a bit faster. So I would like to you understand which techniques, which tools we have got to quantify the human actually error, and how we are doing human reliability analysis, and just giving you a flavor of this. And with that, I would like to stop here and to ask if there is any question.
Thank you very much, Kamal Bey, for such an insightful presentation. We have learned a lot today.
If no question, then thank you too as well, and have a nice weekend. Talk to next week.
Thank you. Have a nice weekend to you as well.